In all the animals that lived in the past, the chalicotheres are the only ones that have really puzzled and interested science. Picture an animal that has the body of a horse, the front limbs of an ape, and long claws that look like scythes where its feet should be. Paleontologists didn't know what to think of them for more than 100 years. Were they movers, tree climbers, impersonators of sloths? These strange animals lived in Asia, Africa, and North America millions of years ago, but they have no living cousins today. Even though a lot of fossils have been found, scientists still don't understand how they moved, ate, and lived. The story of this strange animal makes it look like evolution got drunk and never got sober. The clawed horse that didn't gallop. Think of a horse, but not the kind you'd use in war or for races. Think of one that doesn't have legs but long, curled claws instead. Imagine it walking slowly through old woods, knuckle walking like a gorilla, and stopping to pull whole branches down from trees with arms that look more like they belong in battle than a country trot. There was a chalicothere. It was one of the strangest animals that ever lived. Chalicotheres looked like evolutionary mashups, part horse, part sloth, part ape, and yet related to none of them in a straightforward way. They belonged to the order Perissodactyla, the same group as modern horses, rhinos, and tapirs. But while their cousins ran on hooves and grazed the ground, chalicotheres took a hard left turn down the path of evolutionary innovation. They traded in hooves for claws, and nobody's entirely sure why. Their claws weren't small either. Some species, like Anisodon or Meropus, had claws that extended several inches past the tip of each digit. Long and slightly curved, they looked like tools, shaped for something specific. But they weren't shaped for speed, that much is certain. Chalicotheres were slow. Their limb structure made galloping nearly impossible. Some may not have been able to run at all. So, if you're not galloping away from predators, what are claws like that for? They look like they'd be great for defense, like natural swords that are ready to cut. Surprisingly little proof shows they were used that way. They didn't have very sharp claws, and most of the preserved claw bones don't show any signs of fighting wear, like breaks or stress. Stranger things are shown by the wear patterns. These claws were used over and over to pull. I'm not digging, don't fight, but pulling. This leads to the most popular idea about these strange limbs. Their job was to pull branches. They might not have reached up like giraffes or climbed like sloths. Instead, they might have just stood still, sat on their behinds or knuckles, and pulled twigs down to their mouths. Before trunks or opposable thumbs, prehensile arms like claws were used to move things around. Imagine salad tongs that are much stronger. Their long front limbs, in contrast to their shorter back limbs, only add to this theory. It gave them a sloped, almost slouching body shape, awkward for walking, ideal for sitting or bracing while the arms did the work. Some scientists think they may have even leaned back, resting their weight while the claws went to town. But even that explanation doesn't fully settle it, because not all chalicotheres had the same limb lengths or claw shapes. Some species had claws better suited for digging, but never dug. Others had massive upper bodies and weak hindquarters. It's as if nature couldn't decide what to do with them and kept remixing the design. Another more important question is why claws developed in a group that used to have feet. Most perissodactyls made the tips of their hooves harder so they could run, hide, and stomp their way through genetic pressure. Chalicotheres, on the other hand, don't seem to follow that trend at all. Based on their genetic history, they may have started out with feet like their cousins, but the blueprint was erased at some point. Instead of hard tips, they switched to soft pads and claws that could be pulled back. So, were chalicotheres adapting to something their relatives weren't? Some kind of forest environment where reaching mattered more than running? Maybe they occupied a niche so unique, an herbivore that didn't graze or gallop, but manipulated and browsed, that claws were a better bet than hooves. Whatever the answer is, it clearly worked. For millions of years, these clawed horses thrived across Europe, Asia, and Africa. Still, after all that success, we haven't been able to find a living relative. There was no half-hoofed monkey horse on the loose today to lead us astray. Chalicotheres are no longer there at all. backward walkers of the savannah. You might have thought your eyes were off if you saw a chalico there walking through a Miocene grassland. Their gait wasn't smooth like a horse's run or a gorilla's knuckle walk. It was more like seeing an animal play life backwards, with limbs moving in ways that no modern mammal can quite copy. It wasn't just a matter of stance either. Some paleontologists think that chalicotheres may have walked in a semi-reversed way, putting weight on their limbs in ways that aren't usual for mammals. This idea comes from a forensic approach. Bone wear patterns, fossilized limb bones, when studied closely, reveal how an animal's joints were loaded over time. Scratches, erosion, and microfractures are like footprints burned into the skeleton, telling the story of daily use. And in chalicotheres, those wear patterns are bizarre. In several species, the forelimbs show signs of flexion and pressure distribution that suggest they didn't just bend like a modern ungulate's limbs. Instead, their wrists and knuckles were used in a pattern that may have involved dragging or backward placement before forward propulsion, almost like a reset step before a push. You're not really walking backwards, but it feels a lot like moonwalking through the Miocene. Their strange walk was probably caused by the way their legs were shaped. Chalicotheres often had forelimbs that were too long and hind limbs that were too short, making their bodies slope downward from the shoulders to the hips. Normal four-legged movement was not possible because of the frame's tilt. When you add claws instead of legs, you get a way of moving that has no current equivalent. The best analogies come from gorillas and giant ground sloths. Both walk with bent limbs and use their forearms in unique ways. Gorillas knuckle walk to protect their fingers. Ground sloths lumbered forward with long curved claws, used more for manipulation than speed, but even these comparisons fall short. Chalicotheres weren't built for climbing trees like sloths, and they didn't live in troops or swing through forests like apes. They were solitary browsers in open woodlands and savanna margins. Their bodies suggest motion designed less for speed and more for precision, balance, and strength. In fact, some researchers think chalicotheres didn't walk very far at all. Instead, they may have had highly localized territories, sticking to small zones rich in soft leaves, where their strange gait wouldn't be a liability. The backward step or reset motion might have helped them stay stable while shifting weight between branches or while feeding in awkward positions. It's even possible they developed a way of anchoring themselves while reaching, pressing claws into the ground or bracing against tree trunks. This idea also fits with the strange way their joints work. Their joints don't work like the joints of any live animal with hooves. Some had joint locks that let them rest for long periods of time with their limbs slightly bent but locked in place, which kept their muscles from having to work too hard. Others had ligaments set up in a way that made it look like the front legs could spin or reset in the middle of a step, instead of swinging forward like in a normal walk. Why does this matter? Moving is necessary to stay alive. There are trade-offs in every choice evolution makes with bones and joints. Speed versus stability, length versus power, and flight versus fight. Chalicotheres tried a technique that no other known mammal had. They moved slowly and deliberately while having amazing control over their upper bodies. Nature seems to have backed weird, and weird won. For a while. Gorilla hands, horse heads. If you look at the head of a chalico there, you might think of an ancient horse. It has a long face, wide teeth, and a nose that is made for chewing on plants. Then look down, past the thick neck and slanted shoulders, to the legs. What you'll find there is completely unexpected. Hands that look nothing like horse hands at all. They look more like monkey hands. Those similarities aren't just on the surface. The body has a lot of strange parts. Chalicotheres had hands, not hooves, structured with 5 digits, and the middle 3 were prominent. But instead of ending in flat nails or hooves like most perissodactyls, these digits sported thick, curved claws. The bones of the fingers themselves were robust and articulated in a way that allowed for weight bearing on the sides or backs of the digits. In some species, like Meropus, these limbs were built not just to hold weight, but to maneuver objects, branches, perhaps even entire trunks. It's the kind of setup we associate with manipulation and power, not speed or elegance. When paleontologists reconstructed these hands, they were stunned. The arrangement echoed what we see in modern great apes. Think of how a gorilla walks, placing the middle knuckles on the ground, the wrist slightly flexed, the weight distributed across a curled hand. That's not common in hoofed mammals, and yet chalicotheres, relatives of horses, had somehow evolved toward a similar solution, not for climbing trees, but likely for supporting their bulk while feeding and maneuvering through uneven terrain. The connection brings up an interesting evolutionary question. Why do species that are so different from each other sometimes end up with similar structures? When two different lines come up with the same answer to the same problem, this is known as convergent evolution. In this case, the issue might have been balance and eating while partly standing up. Chalicotheres probably spent a lot of time partially sitting down and using their strong arms to pull down trees or strip leaves, while their gorilla-like hands held up their upper bodies. They didn't walk on their hands and knees like apes, but their way of life made those kinds of arms useful. Their hands are strong, but their teeth suggest they weren't eating anything particularly tough. Their back molars were well developed for grinding leaves, but their front teeth were often reduced or even absent. Some skulls show completely missing incisors. So if they weren't biting off leaves, what were they doing? The best guess is that their lips, gum pads, or possibly even a tongue did most of the foraging once a branch was pulled down. That makes for a strange picture of a creature with the head of a gentle horse and the arms of a bodybuilder gorilla. It would have braced, grabbed and carefully stripped soft plant matter with parts of its mouth that we barely have fossil evidence for. It looks like a baby forest sloth and horse had ape hands. There's even speculation that chalicotheres may have used these hands for display. Sexual dimorphism in limb size suggests males may have had larger or differently shaped forelimbs than females. Did they wrestle? Did they slap trees? No one knows, but their anatomy leaves the door open for some truly strange behaviors. Now we have a creature that is hard to put into a single category. There isn't a clear current box that it fits into, not vegetarian, not climber, not runner. It's just a strange, strong computer with horse-like ears and hands that can grab things. But what kind of animal puts those huge arms down after eating? Some chalicotheres didn't even stand up while they ate. What's next on their developmental journey? They might have looked like the ground sloth, which is one of the weirdest animals ever. The sloth mimic of the Miocene. Now picture something about the size of a modern horse, or maybe even bigger, slouched down on its haunches like a tired gorilla in the hot African sun. Its huge front legs reach up and pull down a leafy branch with their sharp claws. But it doesn't stand up to eat. Instead, it stays sitting, lying on its back like a Miocene couch potato. This wasn't being lazy. It might have been the best way for it to stay alive. And it looks a lot like the giant ground sloth, an animal from the Americas that is very different from this one. For decades, paleontologists struggled to understand how chalicotheres stood, walked, and, more bizarrely, rested. Most large mammals spend their time either on all fours or standing upright on hind legs for short bursts, like bears or kangaroos. Fossil sites show limb and spine wear patterns inconsistent with constant standing or galloping. Instead, the evidence suggests many species rested in a partially upright seated posture, supporting much of their weight on their pelvises and upper hind limbs, just like ground sloths did millions of years later. Their limb proportions support this theory. With long, muscular forelimbs and shorter, stockier hind limbs, they weren't built for chasing or even roaming. They were optimized for bracing, pulling, and sitting. Think of them as biomechanical cranes, using body weight and posture to stabilize while the arms did the work. Fossils from certain Miocene sites, especially in Eurasia, show chalicothere trackways and bone beds clustered near forest margins, suggesting they didn't need to travel far to find food. Instead, they may have claimed a single patch of leafy trees and settled in for the long haul, grabbing meals from a seated position day after day. But this posture wasn't just about feeding. Sitting back on the haunches may have served other purposes too. Thermoregulation, for instance. Large-bodied animals often struggle with heat dissipation. Sitting down in shaded areas, belly against the cooler earth, might have helped regulate internal temperatures. And from a defensive standpoint, it made sense as well. A seated chalicothere had instant access to its strongest weapons, those massive claws and ape-like arms. If a predator approached, it didn't need to flee. It could rear up slightly, swat, or shove. Think of it as a cross between a silverback gorilla and a wrecking ball. The fact that we usually think of ground sloths and sometimes pangolins when we think of this behavior, the sit-and-swipe survival strategy, is what makes it so strange. But chalicotheres had nothing to do with sloths. They were perissodactyls, which means they were related to horses and rhinos, but not to anything from South America. Even though they were in different times and places, they both came up with the same strange answer. When your body gets too big and your arms get too weird, it's better to stay still and bring the world to you. Pelvis and hip sockets that have been preserved add to the puzzle. In some species, these have strengths and turning points that make them perfect for sitting for long periods of time. Some paleontologists even think that the tail, which has long been thought to be an unnecessary part of this group, may have served as a third point of contact, making a tripod with the back legs for maximum support. Once more, very lazy. What does all of this mean? It was chalicotheres who changed what it meant to be a computer. It was interesting to see how chalicotheres built their strange bodies into a fortress while other animals raced across the fields or soared over the forest canopy. They didn't change to get away from everyone else. They changed to be able to control it. Toothless browsers with strange mouths. A chalicotheres skull doesn't look out of place at first glance. It looks like the plan for a typical plant eater, long, horse-like, with a strong mouth and strong teeth. Then you see that something is missing. If you look more closely at the front of the mouth, you'll notice something strange. The incisors, which are the front teeth used to bite and cut plants, are either very small or not present at all in many species. Now picture yourself as a huge plant-eating animal that didn't have any tools to cut leaves off. How can an animal live in a forest with lots of thick plants if it can't bite or tear? In a strange way, the answer might lie in soft tissues like lips, gums, and tongues that you don't see in fossils. Some paleontologists think chalicotheres didn't need teeth to eat at all, based on the shape of their jaws and how they wear down. Instead, they may have used their thick, muscular lips or even their fatty gum pads to delicately and almost deftly pull leaves off of trees. Their molars tell a different story. These back teeth are heavily worn in most fossils, ground down like sandstone from a lifetime of chewing abrasive plant material. This means once the food made it into the mouth, they were definitely chewing. The jaw motion was grinding, not slicing. But how the food got there without front teeth is the real enigma. Some researchers propose that chalicotheres fed in a way more similar to giraffes or camels than to horses. Instead of clipping leaves with sharp teeth, they would wrap their lips around twigs and pull, scraping off foliage with the help of thick gums, or even a hardened dental pad. Others speculate they might have used a muscular tongue, almost like an anteater, to pull leaves into the mouth after pulling branches close with their claws. They may have also evolved more than one strategy, based on the species. Some chalicotheres have small bits of incisors still visible. It's possible that they were used with the lips and gums. The real question is how everything fit together. Because of the upright eating position, long ape arms and awkward gait, a seated, clawed, toothless giant would gently strip trees with their lips and crush leaves with their worn-down teeth. This would be a truly strange way to eat. And that's not just weird, it's unprecedented. Among perissodactyls, even among mammals in general, this kind of feeding behavior is extremely rare. Most herbivores rely on specialized teeth to do the dirty work. Think of beavers, elephants, deer. All have evolved incisors or tusks or grinding systems up front. Chalicotheres went the opposite direction. They got rid of the tools and built the mouth around a whole new process. It's important to remember that not having front teeth also shaped their heads. Their snouts could get longer, thinner, and more flexible if they didn't have to bite. Some chalicothere skulls have small upward tilts at the front of the jaw. This may have been a way for them to better control their lips. It's not heavy, but you can feel it. Evolution was making changes to the model, making it softer and more curved. Belly sitters of the forest edge. People usually think of stampeding mammoths, thunder-footed dinosaurs, and groups on the move when they think of ancient giants. How about chalicotheres? They broke the rule. Some of them might have liked living close to the ground. Fossil records suggest that some species didn't just walk around in woods and fields all day. Instead, they may have rested and even eaten while lying on their backs or halfway on their backs, with their bellies pressed to the ground like statues. The idea of a belly sitter sounds awkward, but it makes evolutionary sense when you look at their body structure. Chalicotheres had long, powerful forelimbs, short and stocky hind limbs, and an overall frame that sloped from the shoulders down. That means standing upright wasn't just difficult, it was inefficient. So instead of staying on all fours, some species may have spent long stretches of time in a semi-recumbent posture, not quite lying down, not quite standing, something in between. There are several ways to look at the facts. First, there is the situation of the rock. Limbs of chalicothere. People have been found tucked under their bodies at some dig sites. Their spines are slightly curved, as if they had just settled down. This is not how most four-legged animals fossilize. When animals die while standing, they fall over in more random ways. But these chalicotheres seem to have died while resting, which means that's how they lived too. Then there's the limb wear data. In many species, the ends of the ulnar and radius, forearm bones, show unusual erosion patterns, as if the animals spent a lot of time placing weight on their forearms at low angles. The wrists and elbows also appear reinforced for pressure applied from above, not just front to back as in walking mammals. Combine that with large padded chest bones and a reinforced sternum, and you get a creature that may have been built to rest on its belly, like a grounded gorilla or a massive reclining panda. But why would an animal pick up this weird behavior? More than likely, the answer comes in saving energy. Chalicotheres were slow. They didn't move around. Because they were big and had slow metabolisms, they probably didn't have to go far to find food. This was especially true if they lived near the forest edge, where they could always reach low-hanging branches and soft-leaved plants. Since you can reach up and pull food down while lying down, why waste energy standing? Herbivores do the same thing, which is weird but very effective. They eat on the couch. This resting posture also might have served as a defensive adaptation. Lying low in shaded underbrush, a chalicothere would be hard to spot, especially in thick Miocene forests where light barely broke through the canopy. And if a predator did get too close, rising from a semi-prone position may have given them just enough leverage to strike with their front claws before needing to flee. It's not fast, but it's functional. This habit of resting the belly is similar to something we've seen in snakes and amphibians, but not very often in mammals. Still, this animal might have gone back to that grounded plan, not because it was weak, but because it was the only way it could stay alive. It also redefines how we think about active versus passive animals. Chalicotheres weren't lazy, they were optimized. Their niche didn't demand sprinting or chasing. It demanded reach, strength, and staying power. That meant building a body not for movement, but for endurance, spending hours in one spot, slowly manipulating the world around them. But don't think that being still means you can't do anything. The parts that are resting, they weren't just sitting around. They were made to have a lot of force, massive force that can pull trees apart, because you don't just wait for the leaves to fall when you have claws like a bear and arms like a silverback. Prehistoric tree pullers. Paleontologists thought they saw the limbs of a digger when they first saw them. It looked like a burrower, long claws, thick upper arms, and shoulders that were strengthened. But the bones showed something else. These things weren't digging into the ground. They reached up into the sky and pulled down the cover. It's true that chalicotheres weren't made to dig. They were made to pull. Studies of preserved limb bones, especially the humerus, upper arm, scapula, shoulder blade, and muscle connection sites nearby, show that these animals had amazing pulling strength, which is not common in mammals. You wouldn't use that kind to lift something up, like a monkey reaching for fruit. You'd need that kind to pull something down, something heavy, like a piece of wood or a whole young tree. Their claws, while thick and curved, lack the tapering or reinforced tips seen in burrowing animals like moles or anteaters. Instead, the stress marks suggest repeated use in forward and downward motions, consistent with gripping and dragging. These weren't claws for breaking earth. They were more like organic grappling hooks. Suppose a chalicothere settles down near a cluster of trees. To keep itself steady, it locks its back legs together and leans against its slanted back. Then it reaches up with its long front legs, hooks a branch with its claws, and pulls down like a winch. The animal gently pulls off the leaves and stems with its lips, gums, or tongue as they fall to the ground. This idea changes everything about how we picture herbivores of the Miocene. While giraffes stretched taller, elephants used trunks, and ground sloths climbed, chalicotheres brought the buffet to them. They didn't adapt to reach the canopy, they adapted to break it. Supporting this are the deeply grooved muscle scars on their scapulae and upper limb bones. These grooves indicate massive muscle attachments, especially in areas tied to pulling motions. Think of the deltoids and lats on a powerlifter. Now imagine those muscles draped over a creature the size of a horse. That's the energy chalicotheres brought to feeding time. Some paleontologists even think that their limbs were built so well for pulling that they didn't need to walk as much. The way they stand, walk, and take strange backward steps may have all formed as a compromise to fit their tree-pulling lifestyle. They were never meant to chase. They were built to hold. This theory also helps explain their geographic spread. Fossils have been found across Europe, Asia, and Africa, regions that, during the Miocene, featured large swathes of woodland or forest edge environments. These were perfect chalicothere habitats, areas dense enough for feeding, but open enough to move and sit. It's the perfect setting for a browser that didn't graze or climb, but pulled. What's even more interesting is how this leg strength is the same across species. Whether it's Anisodon, Moropus, or Tylocephalonyx, the plan is always the same. Thick arms, big claws, short back legs, and a spine that's meant to support and pull. It's like evolution clicked copy on a body made to move trees and never looked back. But even with all of these new ideas, the big question is still why they didn't last. No modern descendants, and no clue why. When you look at the long family tree of animals, most of the branches leave something behind. A cousin who still lives, one that is smaller, a strange branch that is still walking among us. But when it comes to chalicotheres, the tree stops. Few or no straight relatives. There are no tiny figures creeping through modern woods, just rocks and questions. This vanishing act is especially strange because chalicotheres weren't evolutionary losers. They were wildly successful in their time, with fossils found across Africa, Europe, and Asia. From about 40 million to 3.5 million years ago, they thrived alongside early horses, rhinos, and even primates. In some regions, they were dominant browsers, outnumbering other large mammals in the fossil record. Yet while horses evolved into zebras and mustangs, and rhinos adapted to savannas and jungles, chalicotheres just disappeared. Why? One idea is based on the fact that they specialize. The best trick evolution has is also its worst trap. The more perfectly tuned you are for a certain way of life, the more exposed you are when that way of life ends. Chalicotheres were also very specific. Everything about their bodies was designed to help them do one thing: pull down plants to eat while staying still. Long claws, spines that sloped, short hind limbs, and fewer front teeth all work great in thick, safe forests. The world isn't safe, though. The temperature changed a lot as the Miocene ended and the Pliocene began. In Eurasia and Africa, forests started to get smaller. Open savannas and grasslands grew bigger. Animals that could move, feed, and get used to little greenery did best during this change. Speed and adaptability were the new traits that would win. Slow and spread out, chalicotheres couldn't keep up. Another possibility: competition. As forests thinned, other browsers, especially early elephants and giraffes, began to dominate. These animals could travel farther, reach higher, and feed in more dynamic ways. Even some evolving primates began to fill similar niches with greater flexibility. Chalicotheres, with their one-trick limb design and awkward mobility, were suddenly outmatched in a changing ecosystem. Then there's the risk of having children. It's not clear how chalicotheres married or raised their young, But it is known that many big, slow-moving herbivores have fewer babies and longer gestation periods. That works in a world where things are fixed, but when things are changing quickly and there are more predators, that way of reproducing is a time bomb. A whole family can be wiped out by one drought, one disease, or one big population of predators. What makes their extinction even more frustrating is the lack of transitional fossils. Most extinct mammals have some kind of evolutionary breadcrumb trail, ancestors that show slow changes leading to modern forms. Chalicotheres, nothing. It's like they showed up with their weird design, ruled the forests for millions of years, and then walked off the evolutionary stage without leaving a note. There is a wall in even molecular studies. We can't use DNA to find out more about their family tree because they don't have any live straight descendants and none of their close living relatives share all of their traits. Their bones say they are perissodactyl, but the way they live says they are something else. People who have evolved but have been left behind as the world has changed. It's scary and humble at the same time. What does the disappearance of the chalicotheres, a broad and successful group of herbivores, say about all the other species that live on Earth today? Mixed up evolution, odd limbs with hoof DNA. Chalicotheres look like they were made by a group of animals who never came to an agreement. They belong to the same order as horses, rhinos, and tapirs, which are called perissodactyls. In a physical sense, that means they should have feet. For running, kicking, and sprinting across open land, hard keratinized structures formed. Even so, chicks don't have feet, they have claws. That contradiction has puzzled scientists since the 19th century. How did a group of animals descended from the ultimate hoofed herbivores end up with limbs better suited for grappling than galloping? And more intriguingly, why do those clawed digits still carry the genetic hallmarks of hooves? Strange things called evolutionary throwbacks might hold the answer. These are times when a trait shows up again after being lost in the record of evolution. This idea is turned around in chalicotheres. Their clawed digits may not have evolved from scratch. Instead, new study shows that they were changed from hooves. The bones in their fingers and toes still have the sizes and traits of perissodactyl hoofed anatomy deep in their developmental plan. This means their evolution didn't move forward into something new. It reversed course. Hooves, once hardened and reduced to blunt tools for speed, were reshaped into long curved claws, possibly by reactivating dormant genetic pathways from even earlier mammals. Nature went backward to go forward. We see the proof in the bones. The terminal phalanges, the end bones of the fingers and toes, have structural similarities with hoofed ungulates. They're capped in keratin, their cross-sections suggest weight-bearing use, and their joint morphology indicates an origin from an animal that once stood upright on the tips of its toes. Yet in chalicotheres, these bones were elongated, curved, and embedded in soft pads. The result? A Frankenstein fusion between a hoof and a claw. Some species show transitional forms, intermediates between hooves and claws. These fossils offer a rare glimpse into how evolution can remix its own rules. It's not just a matter of gaining or losing traits. It's about retooling old structures for new purposes. For chalicotheres, claws weren't a radical departure from hooves. They were a strategic regression. A return to a more versatile, manipulative tool during a time when forests rewarded reach over speed. This genetic conflict even shows up in the soft tissues. While no muscles or skin survive, the attachment points on chalicothere bones imply a tension between forms. Tendons that would support a stiff load-bearing hoof instead looped around to support flexible curved claws. It's like their limbs were caught between two evolutionary blueprints, one designed for running, the other for grasping. Chalicotheres is a great example of mosaic evolution because of the way that different parts of an organism change at different rates, or even in different directions. Their legs were going back to a more primitive time. Their mouths were coming up with new ideas. Their stance looked like that of monkeys. Their brain was growing in ways that didn't make sense. They didn't change in the same way over time. All of them were different from each other because evolution built them with one foot in the past and one claw in the future. But this biomechanical weirdness wasn't just theoretical, it shaped how they lived. Clawed limbs meant no open plains, no galloping from predators. They needed shelter, places where their strange limbs could shine. Some chalicotheres lived not in the thick forests their claws suggest, but in dry, open regions, places where the trees were sparse but still vital. So how do you survive in a desert if your diet depends on trees? Desert-dwelling giants with forest diets. It seems like a contradiction. A huge, slow-moving plant-eater designed to munch green trees that does very well in the desert. But that's exactly what we can tell about some chalicothere species from fossils. Their bones have been found in old drylands, which shouldn't have been able to support a creature that lived in forests. Still, more and more proof keeps coming in. Pollen samples, tooth wear, and even sediment layers all point to strange settings and unique foods. In several fossil sites across East Africa and Central Asia, chalicothere remains have been found in what were once semi-arid or even arid environments. These were not lush jungles. They were open woodlands, scrublands, and transitional zones where vegetation was sparse, seasonal, and scattered. But here's where things get weirder. Along with the bones, paleobotanists discovered microscopic pollen grains in the surrounding sediment, pollen from trees and shrubs typically found in wetter, more forested ecosystems. Even the wear on chalicothere teeth backs this up. Their molars show the kind of micro-scratches and grinding patterns consistent with soft-leaved plants, not grasses, not tough shrubs, but broad, pliable foliage more common in dense forests. And remember, they didn't have incisors to bite or tear. These creatures were built to strip, mash, and grind tender vegetation. So, how do you explain this difference? One theory is that chalicotheres were experts at living in small spaces. Not a whole forest, just a few trees would do. A group of tall plants, a natural stream that is lined with plants. They could stay alive in areas that were mostly open or dry by going after small patches of plants that looked like forests. Their strange claws and way of eating meant they couldn't change when they were far away, but they were unbeatable when they were near food. Another possibility: climate change was already eroding their ideal habitats, and chalicotheres were the last holdouts. As Miocene forests receded due to global drying trends, they may have followed the shrinking tree lines into drier zones, clinging to what remained. This would explain why some fossils appear in sediments laid down during increasingly arid periods. They weren't adapting to the desert. They were outliving the forest. Some paleontologists even suggest chalicotheres were seasonal migrants, not long-distance travelers like caribou or wildebeest, but slow roamers that moved between reliable water sources and patches of vegetation. They may have spent the wet season in riverine groves and the dry season in sheltered canyons or valleys where trees persisted. In this model, their desert fossils don't show where they thrived, but where they passed through, or where they made their final stands. These desert edge environments may have been death traps. As the forests vanished, chalicotheres likely became more isolated, more vulnerable, and more dependent on vanishing food sources. Their anatomy, once brilliant in a stable ecosystem, became a liability. A massive, clawed herbivore with limited mobility and a narrow diet doesn't fare well in an unpredictable world. That difference, though, between where they were found and what they ate tells us a lot. Chalicotheres were not dumb. They were not beatable relics. They were living things that were stuck in a complicated relationship with a world that was changing. They changed for as long as they could, pushed the limits, took chances. They went to places that no one thought they would go. And in their last few weeks or months of life, they may have been the most complicated they had ever been, with strategic mating, seasonal movement, and strange sexual differences we still don't understand. Chalicothere mating, a mystery in morphology. The most interesting thing about chalicotheres might not be their claws, stance, or walk, but what we don't know about them, especially when it came to how they had babies. Other animals' mating habits can be figured out from live cousins or well-preserved social fossils, but chalicotheres don't leave any clues. No places to nest, no signs of herding, no clear signs of love have been preserved over time. Only bones. But those bones, especially the ones from their heads, tell a very strange story. In multiple chalicothere species, particularly those from the later Miocene, paleontologists have found distinct differences between skulls that appear to belong to males and females. This is known as sexual dimorphism, and it's not unusual in mammals. Think of deer antlers, lion manes, or the size difference in gorillas. But in chalicotheres, the dimorphism is weird. Some skulls are massive, with exaggerated crests and ridges. Others are smaller, smoother, more streamlined. The larger ones show expanded areas for muscle attachment, particularly around the jaw and neck. That suggests strong bite force, possibly for display or combat. But it doesn't add up with their diet of soft leaves. These weren't predators, they weren't fighting for food, so why the heavy cranial armor? One idea is that men compete with each other. Male chalicotheres may have fought over who could mate, just like bighorn sheep or gorillas do. Those skull crests could have been used to hit people in the head or scare them away. The muscle mass would help keep the neck stable when the animal hit something, so it could take blows or swing its head sideways to slap. Giraffes still do this during necking fights. Unlike most mammals that use antlers or tusks for showdowns, chalicotheres already had built-in weapons, their claws. So why fight with heads when your arms are literal tree-pulling death tools? That's what makes the dimorphism so strange. It suggests that claws weren't used for intraspecies combat. Instead, fights, if they happened, may have been highly ritualized. A dance of posture, size, and bluffing. Those big skulls? They weren't battering rams. They were status symbols. Another idea is that the differences in skulls had nothing to do with fighting and everything to do with sound. Some of the bigger sinus spaces and brain chambers in bigger skulls might have worked as resonance chambers, sending bellows or calls over long distances, like when an elephant rumbles or a howler monkey screams. Male chalicotheres may have used noise to mark their area, find mates, or scare off rivals from away. Their woods may have been filled with deep, groaning sounds that aren't made by any living thing today. There's also evidence that their mating system may not have been monogamous. The pronounced size and shape differences between sexes hint at sexual selection, where one gender, usually males, evolves flashy traits to impress the other. If that's true, female chalicotheres likely choose mates based on physical traits, skull shape, claw size, or even scent. But again, no living species mirrors their exact biology, so we're working from shadows. Fossil sites also show no clear herding behavior. Unlike horses or elephants, chalicothere remains are rarely found in large groups. That could mean they were solitary for most of the year, only coming together briefly to mate, like modern bears or tapirs. If true, courtship might have been intense and short-lived, with males competing hard and females choosing fast. Their love life is still one of the most frustrating unsolved mysteries in geology because we don't have more full fossil records, soft tissue impressions, or behavioral clues. They didn't have enough successful matings to keep them from going extinct, no matter what those habits were. The disappearing giants of Asia and Africa. Chalicotheres didn't just go away. In the past, they lived all over the world, from the thick woods of Europe to the open forests of Africa and the rolling hills of Central Asia. Megafauna like rhinos, elephants, and even big monkeys were all changing at the same time, and they were able to keep up for millions of years. Then it looked like they were gone all at once. There have been a lot of strange disappearances of mammals in the past. These weren't fringe creatures barely making it by. They were the main feeders in some parts of Africa and Asia. Fossils from those times show that the populations were healthy, there were many species, and they lived in a lot of different places. What happened? The timeline offers the first clue. The last chalicotheres vanished around 3.5 million years ago, near the close of the Miocene and the beginning of the Pliocene epoch. This was a period of rapid environmental change. Global temperatures dropped, ice sheets expanded, rainfall patterns shifted, and perhaps most importantly, forests began retreating. In Africa, tropical rainforests gave way to patchy savannas. In Asia, temperate woodlands fractured into scrub and steppe. The lush, closed canopy environments chalicotheres relied on started to vanish, replaced by open grasslands where food was tougher, faster to decompose, and spread farther apart. For most herbivores, this wasn't the end of the world, it was an opportunity. Horses, antelope, and early elephants adapted quickly, evolving stronger teeth for grazing, longer legs for migration, and more efficient digestive systems. But chalicotheres had bet everything on one strategy: stationary browsing from branches. Their claws, limbs, and posture made them masters of leafy forests. But in a world of scattered trees and fast-moving herds, those same traits became liabilities. Their size worked against them too. Large animals need large food supplies, and in a landscape that was drying out and thinning out, finding enough tender foliage to fuel a giant became harder and harder, especially for creatures that couldn't travel long distances or switch diets on the fly. Competition played a role as well. As hominins began to evolve in Africa and spread into forest margins, they may have disrupted ecosystems further, either through fire use, predation, or simply altering the delicate balance of forest regeneration. Other browsers, like elephants and early giraffids, may have outcompeted chalicotheres by being more flexible in both diet and movement. And then there's the reproductive angle. If chalicotheres truly were solitary, or had complex mating systems dependent on narrow windows of contact, their populations could have been extremely vulnerable to sudden environmental stress. A few failed mating seasons, due to drought, habitat fragmentation, or migration mismatch, and a local population could collapse. Multiply that across a continent, and extinction wouldn't take long. Still, the whole thing about their absence is what makes it so scary. Islands don't have any tiny chalicotheres living there. There are no fossils in the Holocene layers. There were no strange offshoots trying to fit in with the new world. Nothing but silence. It was made by other perissodactyls. Horses raced to the top of the world. The rhinoceroses changed. In humid jungles, tapirs stayed alive. How about chalicotheres? They were the risky bet on evolution that didn't pay off. Not a single disaster, though, wiped them out. Not a rock. No winter with volcanoes. There was no mass catastrophe. Everything they needed to stay alive was slowly being taken away. A death by 1,000 changes in time, place, and temperature. Their absence today leaves a weird hole in the mammalian family tree. We have no direct analogues. No living animal captures the full strangeness of their lifestyle. Nail-like claws, but no digging habits. When people saw chalicothere fossils for the first time, especially those huge bent claws, they immediately thought that the animals must have been digging animals. These days, big curved claws are generally used for one of two things: digging into the ground or pulling apart food. But chalicotheres didn't dig holes. They were also not hunters. What were these huge hands used for? First, let's talk about what they weren't used for. Even though their claws look like those of moles or anteaters, chalicotheres don't have any special bones that help them dig well. Their wrists aren't designed to push down hard enough to break through the ground. They don't have the thicker wrist bones, tight arm muscles, or shovel-shaped hands that real diggers do. Their claws are very long, but they aren't as strong as the claws of animals like badgers and pangolins. They are also pretty thin and easily broken. There are also no fossil burrows attributed to them. No collapsed dens or tunnel networks that would suggest they dug for shelter or food. These were surface-dwelling giants, more likely to rest under a tree than inside a hole. What did they do with those claws when they weren't digging or hunting? Most people agree on the idea that they feed by reaching up, hooking limbs, and pulling them down. We looked into that. It's not the whole story, though, because the tips of the claws were often rough, making them look more like nails than swords. That kind of wear pattern suggests that the animal has been in close quarters with hard objects like bark, rocks, or even other animals. Thus, another choice comes up: defense. Picture a chalico there in a clearing in the woods. It's not quick, it can't hide from danger. It can, however, swing and sit back on its hind legs. Their claws could be longer than half a foot, and their arms are as long as a person's. A full-strength swipe could really hurt them. They weren't killers like cats or bears, but they could hit with strikes that would break bones and smash branches, making any attacker think twice. And this might be why those claws never evolved into blunt hooves or vanished entirely. They were dual-purpose tools, used both for pulling down food and defending that food and themselves from threat. Their anatomy suggests leverage, not speed, power, not precision, the kind of mechanics built to hold the line rather than flee. There's another theory that pushes things even further: visual intimidation. In many species, exaggerated body parts serve to scare off rivals or predators without actual violence. Think of the gorilla's chest beat, the porcupine's quills, or the cassowary's clawed kick. Chalicotheres may have used their claws, and the act of displaying them, as a bluff. Rising up, arms wide, claws extended, they would have looked massive and menacing, even if they rarely struck. Fossil forelimbs from some individuals show minor fractures and healed breaks, possibly from falls or even clashes with other chalicotheres. These weren't constant fighters, but when the situation called for it, they had the gear to hold their ground. But there is still no smoking gun. Animal remains don't have claw marks on them. As preserved velociraptor duels go, there are no skeletons locked in fight, just put on patterns, just possible outcomes. It's clear that the claws were very important to their survival, not as weapons of war, but as useful tools that they used to eat, send signals, and stand their ground when they had to. And we need to dig deeper to figure out why that's such a strange mix. The chalicotheres' claws were weird, but so were their joints. The way they stood and moved was also strange. They couldn't bend their legs like a horse or even an ape. Their joints locked, turned, and stretched in ways that were not normal for mammals. Strange joint locks and limb posture. The more you learn about chalicotheres, the more it seems like they were made from different sets of plans. When you look at their joints, that's most clear. To put it simply, chalicotheres did not walk or stand like mammals do today. The way their legs are positioned, how their weight is distributed, and the way their joints are built make them look nothing like horses, apes, sloths, or any other living thing that looks like them. It's like evolution was playing around with engineering, playing around with different ways to move through space without ever deciding on a clear design language. The most important feature is a joint that locks in place. There are many types of chalicotheres, but the later ones like Anisodon and Meropus have bones in their wrist and elbow that look like they have complicated locking systems. The radius and ulna, which are the bones in the wrist, don't connect in a smooth, rotating hinge like in most four-legged animals. They sit together instead, partly fused and weight-bearing, in a way that says they can't move much but are very stable. Picture a tripod that isn't bent, but doesn't need to be. This locking function likely served two major purposes. First, it allowed chalicotheres to brace themselves for extended periods in one place without using active muscle strength, perfect for an animal that fed in seated or crouched postures, pulling branches down with its claws. Second, it gave them defensive leverage. A chalicothere didn't need to spring into action. It needed to hold its ground, rooted like a tree, while swinging its front limbs with brutal force. The hip and shoulder joints were strangely bendy, but only in certain directions. Chalicotheres don't have a full range of motion like apes do, or a limited front-back hinge like horses do. Instead, they have a strange mixed range of motion that limits their forward step, but allows them to move very easily laterally and downwardly. So set up that it doesn't make sense to run, but it makes perfect sense to feed while standing still and reaching left and right, or pulling branches at strange angles. Then there's the knee and ankle situation. Their hind limbs were short and stocky, and the knees bent in a way that placed the body in a permanent slope, from tall shoulders down to low hips. This posture isn't unique to chalicotheres. It's also seen in gorillas, but the comparison only goes so far. Unlike knuckle walkers, chalicotheres didn't use their hands for locomotion the same way. Instead, they may have adopted a semi-digital stance, resting on the backs of their knuckles or claws in a crouched, shock-absorbing gait that was slow but surprisingly stable. A lot of new reconstructions show that chalicotheres didn't walk at all like current four-legged animals. They might not have taken smooth steps, but rather steps where their weight was moving back and forth, carefully putting each limb before shifting again. It would have looked weird, maybe even sloppy, but it worked for them in the woods. This slow, careful way of moving is supported by their very own spinal column. Chalicotheres had relatively stiff backbones, especially in the lumbar area. This was different from sprinting animals, whose spines were very flexible for speed and recoil. The fact that their spines can't bend all the way back adds to the idea that they weren't made to run, but to hold, brace, and pull. And this matters, because movement is destiny in the animal kingdom. It shapes diet, defense, reproduction, everything. Chalicotheres weren't just shaped by what they ate, but how they stood while eating. Their whole body plan was a commitment to a way of life that involved almost no motion. They evolved to become living feeding stations, fortresses of muscle and bone planted in place, moving only when absolutely necessary. Living fossils of the past, chalico the lookalikes today. No one is related to chalicotheres. In the evolutionary tree, their branch comes to a sharp end, leaving no twigs or offshoots to carry on their work. But nature has an odd sense of when things have happened before. Evolution sometimes goes around in loops, making echoes of extinct species in completely different families, even when there is no straight lineage. And when scientists and artists try to picture what a chalicothere might be like when it moves, or in spirit, they think of a few well-known people. Start with gorillas. They're not close relatives at all, primates instead of hoofed mammals, but the similarities are hard to ignore. Both are heavy-bodied, slow-moving, and equipped with long, powerful forelimbs. Gorillas knuckle-walk through forests, using their arms as both locomotion and support. Chalicotheres didn't knuckle-walk in quite the same way, but the wear on their limbs and the mechanics of their joints suggest a similar forward weight distribution. Their hands weren't just for movement, they were for control, for manipulating the world around them. The similarity is more in-depth in how they act. Gorillas eat quietly while sitting or leaning in one place for most of the day. They only move when they have to. This way of life saves energy and works well for big, slow-moving animals that live in places with lots of resources. Chalicotheres probably did the same thing. They hung out at the edge of a forest patch and drew food to them instead of going looking for it. Now jump to giant ground sloths, the long-lost South American titans of the Pleistocene. These creatures, now extinct, are the best behavioral analogues to chalicotheres we have. Sloths also had long claws, not for killing or digging, but for pulling branches, trunks, and foliage into reach. Their gait was awkward, their posture semi-upright, and their movement slow but deliberate. Like chalicotheres, they often sat back on their hindquarters to feed. Like chalicotheres, they were poorly suited for running, but masters of patient, powerful manipulation. People are arguing about the similarity. If two species that are not related at all and lived millions of years and on different continents developed the same way of eating and the same shape of their limbs, that way of life might be connected to a greater ecological need that still remains today but isn't being met. Next is the tamandua, which is also known as the smaller anteater. Despite being very small and having nothing to do with each other, they still have long claws, an awkward shuffle, and a stance that makes them good at pulling branches off of trees and selectively eating. It shows that behavior doesn't always change in the same way over time. An animal that weighs 100 pounds and one that weighs over a ton can sometimes share the same niche. Even pangolins and aardvarks, both of which use their claws for very different reasons, digging, foraging, defense, show how claws and posture can converge again and again when circumstances are right. But none of these animals are truly chalicothere-like. They're approximations, reflections, attempts by nature to test similar blueprints in different times and places. We can't help but think, what if, when we look at them? What if a chalicotheres was still alive today? It would likely be moving through a bamboo forest, stopping at the edge of a clearing and rising on its hind legs to carefully rake down branches. Would it look strange? Could we tell it from the way a gorilla's shoulders are hunched, a sloth's claws that look like bears, or a tamandua's slow-moving ease at lunch. Seasonal molting in a mammal? We usually think of snakes, birds, and insects when we think of molting, scales flapping off, feathers falling out, and exoskeletons opening up. In terms of mammals, changes in fur thickness or spotty shedding in the spring and fall are usually the only signs. Still, skin marks found in fossils at a few very rare chalicothere sites suggest that these huge ancient animals may have gone through something much stranger, something more exciting, a possible type of yearly molting that is different from what we see in big cats and dogs today. In a small number of Miocene sites, particularly in Eastern Europe and parts of Central Asia, paleontologists uncovered fossilized patches of chalicothere skin. These impressions, pressed into sediment and preserved by luck and geological chance, show unusual textures. Instead of the fine hair impressions or scaly patches seen in other species, chalicothere skin shows large, irregular surface patterns with what appear to be shallow follicle pits arranged in complex waves. The structure of these impressions has led to speculation that chalicotheres may have shed their outer layer of skin or fur in large patches, possibly as a seasonal adaptation to changing climates. Why do they need to shed their skin? During the Miocene, there was more than one long, lush jungle. Temperatures rose and fell, and it rained and dried out many times. For a big animal that doesn't do much and has trouble controlling its temperature, losing its whole hair in the spring or fall might have been a way to keep from getting too hot, getting parasites, or even getting fungal diseases. Especially if they rested on their bellies for a long time on the ground in the shade where the humidity could be high. Some experts have pointed to elephants and hippos as modern comparisons. While they don't molt in the traditional sense, they do shed skin in chunks, develop seasonal calluses, and undergo surface regeneration in response to environmental changes. Could chalicotheres have had similar physiology? Thick, partially hairless skin with patches of fur that came off in waves? It's not hard to do. Because of their size, they couldn't have worn normal animal clothing in the warmer months. Because they lived on the edges of forests in the shade, they may have needed extra pieces of clothing when it was cold, but they had to take them off quickly when it got warmer. The idea of molting is also linked to possible social actions. Could molting have been linked to mating shows or control if it happened at certain times of the year? For some birds and animals, molting happens at the same time as breeding. This gives them new skin, scents, and signs. Could a male chalicothere that had just shed its feathers have been more attractive to a mate? Or could skin flakes and fur that has been shed have been used to mark territory or let animals know they were ready to go? We don't know. No direct evidence links molting to behavior, but the strange skin textures remain. And for a creature already packed with contradictions, molting fits right in. A horse-shaped sloth gorilla that sat down to eat and possibly shed its skin like a snake. Even though the thought seems crazy, it pushes us to face the bigger truth about chalicotheres. There aren't slightly off copies of animals we know here. We're working on tests in evolution. Aliens with claws instead of hooves, lips that ate without teeth, and skin that may have peeled off with the seasons were experiments in biology. Chalicothere, brain cases, small heads, big sensory lobes. It's simple to think that the animals with the strangest looks were also the dumbest. At first look, chalicotheres seem to back up that idea. Because their heads are often big in the jaw and long in the nose, there isn't much room for their brains. Their brains were small compared to their bodies, small even compared to the brains of other eaters. But here's the catch. Paleontologists aren't interested in how big the brain was. It's because the parts were too big. When researchers created endocasts, internal molds of the brain case that reflect the brain's shape, they discovered that chalicotheres had unusually enlarged olfactory lobes and optic centers. In other words, their brains were optimized for smelling and seeing. Let's start with olfaction. The olfactory bulbs, which process scent signals from the nose, were surprisingly large in proportion to the rest of the brain. This suggests that smell was a primary sense, perhaps even more dominant than in many modern hoofed mammals. It supports the idea that chalicotheres were selective foragers, relying on scent to locate specific types of leaves, flowers, or fruits in dense environments. In forest margins, where visibility might be limited and food patches scattered, a powerful nose would be essential. But scent may have had a social function too. If chalicotheres were solitary or only came together to mate, then scent trails, territorial markings, and pheromone detection would be vital for finding others of their kind, especially in a landscape full of other large herbivores competing for space. Then there's seeing. Even though chalicotheres had small brains, their optic lobes were bigger and their orbital openings were wider, which suggests they had big eyes and advanced vision. This doesn't happen often in computers that move slowly. Most big animals use their wide-angle vision, not their ability to see fine details, to find predators. But chalicotheres may not have needed good eyesight to avoid danger. They may have needed it to find their way through the small world of tangled trees, dim light, and slight signs of movement. Picture yourself as a huge animal sitting in the dim light of the edge of a forest. You don't move much, but to stay alive, you need to be able to see the twitch of a branch, the flicker of movement in the sky, or the glow of ripe fruit in a sea of green. Not a lot of brains, but great depth awareness and contrast sensitivity are needed for that. Even though their brains were small compared to their bodies, they weren't simple. The cerebellum, which controls balance and fine motor skills, was fully developed. This may have been because they had to use strong limbs to feed, which needed precise control of their muscles. To pull down trees with claws longer than your fingers, you must be very careful not to miss. That refined motor control might also explain how chalicotheres avoided injury despite their unusual posture, coordinating long forelimbs, a sloped back, and joint-locking limbs without toppling over. That takes nuanced internal calibration. The brain may have been small, but it was doing highly specialized work. All of this changes how we think about these creatures. They weren't stupid tanks. They were experts in their senses and were tuned into their niche in ways we're still trying to figure out. They didn't have to be able to solve problems like crows or find their way like wolves in order to stay alive. They had to be very aware of what was going on around them, picking the right branch, following the right smell, and being careful not to take the wrong step. They may have been sensitive to how they engaged with each other as well. It's likely that smells, sounds, and body language, from mating shows to territorial behavior, carried more meaning than we can figure out from bones alone. In a strange way, those early scientists missed those same tiny clues, because no one thought of gentle giant or forest feeder when chalicothere bones were first found in the 1800s. Victorian-era monster mislabeling. When chalicothere fossils were first found in the 1800s, scientists were still trying to figure out what extinction meant, let alone the idea that strange, one-time-only life forms used to live on Earth. So, paleontologists had nothing to compare the skeletons to when they found ones with the body of a horse, the claws of a bear, and the head of a very big gorilla. They did have imagination, and there was a lot of it in the Victorian age. Early reconstructions were nothing short of monstrous. Artists and scientists alike drew chalicotheres not as awkward browsers or forest giants, but as predators. One early depiction even showed a chalicothere lunging forward on all fours, claws bared, fangs inserted where none ever existed. They looked like nightmare fuel, saber-toothed apes crossed with demon horses. Some even labeled them as prehistoric satyrs, drawing from myth rather than morphology to explain their strangeness. This was partly because of how the bones were found. Chimeras with heads from one species, claws from another, and jaws turned upside down were made by putting together pieces of bodies that were not whole. You make up stories in your head when you look at a claw that is broken up and the size of a human hand, with no current example of how it was used. At the time of Darwin and the dinosaur craze, those holes were quickly filled with monsters. Even well-known experts made mistakes. One early naturalist called it a clawed horse that ate meat and thought that the animal used its arms to cut up its food. Another person thought it was some kind of lost ape-horse cross, which was a horrible mistake made possible by the fossil's big upper limb bones and strong shoulders. Some reconstructions put chalicotheres on their backs like gorillas, while others spread them out like alligators. No one could agree on whether they were hunters, hikers, or something else. These misunderstandings weren't limited to illustrations. Museum exhibits in the late 1800s featured chalicothere skeletons posed mid-lunge, claws extended in permanent threat. It wasn't until the early 20th century that more complete skeletons and better context revealed the truth. These weren't killers. They were specialized herbivores, more concerned with pulling down branches than tearing into flesh. But the harm was already done. The story of the monster stuck, especially in early geology books and public media. Chalicotheres were used as minor bad guys in science fiction and fantasy stories, with drawings and books showing them as old top predators that never let go of their claws. The truth that they were slow, maybe shy, and fed along the edges of forests wasn't as interesting. In a strange way, the things that led to wrong ideas about them, those claws, their sloped backs, and their mixed look, are now what make them so interesting. They were never scary. People didn't understand them. Today, with modern scanning, 3D reconstructions, and biomechanical modeling, we've corrected the record. But even now, chalicotheres remain elusive in the public imagination. They're not famous like mammoths or saber-tooths. They don't show up in kids' books or Jurassic Park spin-offs. They're the overlooked giants, too weird to fit the mold, too peaceful to fuel legends. That may be what makes them unique, because chalicotheres were not like other people in an age of hunters and prey and survival of the best, like a living riddle, a quiet protest against what it means to be a big guy. Not hunters, do not run, but slowly moving, sense-driven beings that did best when they drew the forest toward them and then disappeared before anyone could figure out what they were. They were never meant to win by speed or fear, but by being still, strong, and having a strange beauty. Chalicotheres broke every rule about what an animal should be like. They lived for millions of years and had no modern counterparts, but they died out before we ever saw them living. In a world full of big cats and flashy skeletons, their story is a quiet warning that the strangest animals sometimes leave the most mysterious clues. Sign up, like, and come along with us on our next trip into Earth's strangest past if you want to learn more about lost giants, evolutionary puzzles, and prehistoric oddities that change what we think we know.